Hello and welcome to Math with Mrs. Becker. Today in Calculus, we are going to look at the second half of section 3.2, which gives us another angle or another version of how we can use the chain rule. So just as a review, the chain rule allows us to find the derivative of composition functions. Now, when we looked at the first part of 3.2, they gave us the formula that says you take the outside of the composite function, you find the derivative. Where the variable is, you replace it with the original inside function, or g of x, then you multiply it by the derivative of g of x. This is what we practiced the first part of 3.2, okay? Now, sometimes when you're working with application problems, story problems, what occurs is that you have so many different variables that you need a separate way besides this method to find the derivative, okay? And so that's why we'll have a second method for doing the chain rule, okay? Now this one, as you first look at it, it does seem a little confusing. After we do a couple, I promise it'll make more sense, okay? So it says there is another way to write the chain rule. Often you're using this when we're dealing with story problems, which we will look at momentarily. Given the function, that is a composition function. That's what the chain rule is used for. Rather than having g of x, they name it u. So they give it a totally separate variable. That way, now you have y equals f of u. Okay, so rather than looking at the full function, they just replace it with the u. Then what can happen is when you go ahead and find the derivative of the separate pieces. If you're finding the derivative of u, the variable is an x. So it's the derivative of u with respect to x. Okay, that's the derivative. Then when you're finding the derivative of y with respect to u, because your variable is a u, you would have this. Now what this allows you to do is I can take these two things, the derivative of u with respect to x, the derivative of y with respect to u. If you multiply those things together, we can cross-cancel du. So I end up with the derivative of y with respect to x. So it is kind of cool, you guys. So it's a separate way to look at this. Let's go ahead and do a few problems and see if we can make some sense of this craziness, all right? So just to practice the skill, if we have y equals u squared minus 2u cubed plus 8. And we have u equals x squared plus 1. If we want the derivative of y with respect to x, well, what's going to happen is you have to find the derivative of each piece. Because if I find the derivative of this would be the derivative of y with respect to u. If I find the derivative of this, it'd be the derivative of u with respect to x. So in order to get the derivative of y with respect to x, it's a combination of these two. So if I take the derivative of y with respect to u, because it's y equals and my variable is a u, your derivative is 2u minus 6u squared, okay? The derivative of u with respect to x, the derivative of u, the variable is an x. This is 2x. Now what they want you to realize is we can find the derivative with respect to y by multiplying these together. And I can show that by taking the notation, the derivative of y with respect to u times the derivative of u with respect to x. This cross cancels, so what we would have is the derivative of y with respect to x. And that's what we're looking for. So if you can multiply the two notations to get that, that means we can multiply the two derivatives as well to get that. So 2u minus 6u squared times 2x. Okay, so what I'm going to go ahead and do here is multiply them. So I would have 2u times x, 2 times 2 is 4, I have an x and a u, minus 6 times 2 is 12, I have an x and I have u squared. Okay, so I multiply the two together. Here's the problem. They only want our variable to be an x. That's what this notation tells us. Well, we know that u is really x squared plus 1. So now I can go in and use that substitution property. That's a rule that we have used all the way back since like 8th grade algebra. I can replace u with what it's equal to. So I would have 4x. U is really x squared plus 1. Minus 12x, u is really x squared plus 1 squared. Okay, so again, I found the derivative of y with respect to u. I found the derivative of u with respect to x, so I found the two derivatives. By multiplying them together, we can cancel du, leaving us dy over dx. So I multiplied them together. It was 2 terms by 1 term. So I distributed. I got it to here. However, with this notation, we know we're only allowed to have x's. So at this point, I saw that I had u's. I only want x's. U is equal to x squared plus 1, so I substituted x squared plus 1 in for u. So here would be the setup. Now at this point, I could go ahead and simplify it more if I wanted to. To be totally honest, I would be okay if you left it here. Some people I know would want to go further, so I'm just going to go ahead and show you what that would look like. But again, if you got it to here, you're fine, because you only have x's in the problem. Let's say you wanted to go further. I could go ahead and distribute, so this would be 4x cubed plus 4x. Then it'd be minus 12x. The only way to distribute that is we'd have to go ahead and FOIL this. Because it has a power of 2, order of operations, you'd have to do the exponents first. So x squared plus 1, I actually have 2 of them. X squared times x squared is x to the power of 4. X squared times 1 is x squared. X squared times 1 is x squared. When I combine like terms, I'd have 2x squareds. Last, 1 times 1 is 1. Now I could go ahead and distribute, because order of operations, you have to do exponents before you can multiply. 4x cubed plus 4x. This would be negative 12x to the power of 5. This would be negative 24x cubed. This would be negative 12x. So your derivative of y with respect only to x, I could go ahead, combine any like terms. I would have negative 12x to the power of 5. 4 minus 24 would be negative 20x cubed. 4 minus 12 would be negative 8x. That would be a simplified version. Okay, and the reason why I'm showing you both, as you're doing the problems in the back of the book, sometimes they stop here. The bonus for stopping here is you can see the setup of everything. You could see that you distributed the 2x. Then you just replace the u's with x squared plus 1. Okay, so that's fine. The benefit of this is a whole lot easier to understand than this. When you're looking at it, this looks pretty intense, where this looks like, hey, you're used to seeing something like that. Either option is good to go. Okay, one is not necessarily better than the other, so it's important that you understand that. That way, if you compare answers with another classmate or you check your answers in the back of the book, you realize that both of these answers are correct. Okay, let's go ahead and look at why on earth do we need a whole nother way of doing this, okay? In many situations involving compositions of functions, the basic variable is time, and that could be years, minutes, days, any increment of time. It may happen that x is a function of time. So you might have like x equals g of t. So it's x equals, and your variable is a t, so you could find the derivative of x with respect to t. Some other variable, let's say it's r, like revenue, is based off of the number of units. So r is f of x. Then you could go ahead and make a composite function. But what happens is right now revenue is based off of x. Here, the number of units would be based off of time. By finding the two derivatives separately, you could multiply them, cancel the units, and you could figure out what is your revenue based off of time instead of the number of units. Okay, so it's allowing us to get rid of the middleman. Okay, let's look at a couple examples. A store sells ties for $12 a piece. Let X be the number of ties sold in one day. Let R be the revenue received from the sale of X ties. Okay, so revenue is 12 times X. Remember, revenue is the amount of money that you're collecting. So it's $12 times the number of ties that you make or you sell, okay? If daily sales are rising at the rate of 4 ties per day, how fast is the revenue rising? So X is the number of ties. It's rising at a rate of 4 ties per day. So that's its slope. It's rising, so it's a positive 4 per day. Day, that is an increment of time. So our revenue is $12 per tie. The number of ties that you're selling is increasing, so it's a positive 4 ties per day. we want to know how fast the revenue is rising. So we want to know revenue based off of time. So if I find the derivative of R with respect to X, sorry about that, X because that's what the variable is, the derivative of 12X is 12. The derivative of X with respect to T, and the reason why it's with respect to T because that's your variable. The derivative of 4T is 4. Now, if I multiply this derivative of R with respect to X times the derivative of X with respect to T, this would cancel this. So my answer would be, how does the revenue change based off of the time? So I multiply these two together. So I can take 12 times 4. That is 48. It's the revenue, so it's money. It's $48 per time unit, so per day. So what's happening at this point is you can expect to earn an additional $48 per day. So it's really cool to help us with story problems. Here's another one. We're going to step it up a little bit more. The demand equation. Remember, demand equation tells you how you should price something. So the demand equation for a certain brand of graphing calculator is P equals 86 minus 0.002x. P is the price of one calculator in dollars. X is the number of calculators that are produced and sold. Determine the time. Okay, so we're looking for T. The time rate of change if the total revenue of the company increases production by 200 calculators per day when the production level is 6,000 calculators. Okay, so revenue. We want to know the total revenue. Revenue is X, the number of items, times the price. Well, you guys, this time the price is another function. So our revenue is X times P, where P is 86 minus 0.002x. So I distribute. So revenue is 86x minus 0.002x squared. That's your revenue. So I could find the derivative of R with respect to X. Then they're telling us that the company increases production, so X, the number of units of calculators, it's increasing, so the slope is positive, 200 calculators per day. So it's 200 positive per day. Day is an increment of time. So let's go ahead, find the derivative of R with respect to X. This is 86 minus 0.004x. The derivative of X with respect to T is 200. Now, when I combine these, if I take the derivative of R with respect to X, which is this value, and I multiply it by the derivative of X with respect to T, I'm no longer looking at the number of units. What I'm looking at is the change in revenue based off of time. That's what I want. So I'm going to go ahead and multiply these. So it's 86 minus 0.004x times 200. Okay, I'm multiplying the two derivatives because that's what I want to know. I can go ahead and distribute because this is one term times two terms. 86 times 200 is 17,200 minus 200 times 0.004 is 0.8x. Now here's the deal, you guys. This is what you get when you multiply them. This tells us we only want the variable to be a t. Well, x is really 200t. So I need to go ahead and substitute that in. So it's 17,200 minus 0.8 times 200t because it's based off of t. So I have 17,200 minus 160t. So there is the derivative. Now we're not done, okay? Let's go ahead and keep looking, okay? So this is the derivative. This is the change in revenue based off of time, okay? Now it says when will the production when the production level is at 6,000 calculators. So what we have to do is figure out the time when this equals 6,000 calculators. So once you find the derivative, they're telling us that the production level is 6,000 calculators. So we set it equal to 6,000. We want to know, determine the time. How many days, because that's what our time increment is, when the production level will be at 6,000 calculators. So now I'm just solving. If I minus 17,200, I would have negative 160t equals negative 11,200. Divide both sides by negative 160, and t would be 70. And remember, t is increment in days. So this is just another look at the chain rule. Rather than using this formula like we looked at in the beginning of the section, being able to do two different variables, multiply them together, we can cancel out a variable, so you can do things like look at the revenue based off of time. Same thing here. We looked at the revenue based off of time, even though the information we had was based off of X. So the chain rule allows us to do some of those cool tricks when we're looking at application problems. Again, I picked a few good questions out of the book so you can practice the skill. You want to go to page 213, 214, 37 and 38, 45, 47, 51, 53, 54, 56. I kind of jumped around and just picked ones that I thought were good. There's 8 questions total. What it will do is just really kind of expand your knowledge on the chain rule and give you a little bit more confidence the more you practice. I hope you enjoyed the second part of 3.2, and I look forward to talking to you soon.